Okay, hi guys. Welcome to the first AP Bio notes video that I have ever made. I'm really excited that you are here and watching and hope it's great. Let me know, of course, after you watch if you have any feedback. This week we are talking about basic chemistry, which should be a review, and properties of water, which should also be a review. But just because it's a review also doesn't necessarily mean that you remember it. So I'm going to go over it kind of quick, but if you have questions or anything like that, just let me know and I'll be happy to talk it out with you. Our first unit in here is biochem, so that's why we're starting with this. And this video is going to be broken down into two videos, actually. The first one will be this basic chemistry review, and the second part will be water. I also sent you the blank slides of this into OneNote. So what I might recommend doing is maybe watching this video on your phone or on a second computer and pulling up OneNote so that you can actually like write on your slides as I write on my slides. Just the way that I found is best for me to take notes throughout like all my years of educating. So it's what I'm going to recommend to you, but that doesn't mean you have to do it. You can do it however works for you best. So, okay, here we go. Let's see if we will. There we go. It's a little too. Okay. All right. So we're just going to start out really basic, talking about just the chemistry of living things, elements versus compounds. Elements, of course, are like the pure substance. They're all the little squares on the periodic table. And then your compounds are combining those elements through chemical bonding. So this would be combining elements using chemical bonds. I don't know why I don't want to write the right letter. Bonds. Examples of elements are your regular carbon, oxygen, nitrogen, the whole periodic table. And then compounds are going to be things like water, salts, sugars. And compounds are going to be more important for what we're talking about in AP Bio this year. We're going to be focusing on pretty big molecules, even in our biochem unit, and then, just getting bigger from there. So there you go. In living things, which is what we care about because this is biology, there are about 25 elements that are used. The other ones might be just like trace elements, but for the most part, it's these 25. And then there are 6 that make up like, I think it's 98% of living things. And they spell schnapps, which I realize is not a word, but they spell it anyways. So it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And most of those are going to be ones that we talk about a pretty decent amount this year. We won't talk a whole lot about phosphorus and sulfur, but the other ones are a big deal. So those are the elements that make up the majority of you, and also the majority of all the other living things on the earth. So from there, let's talk about atoms. Atoms are the smallest unit of an element, and they're composed of your friends protons, neutrons, and electrons. And then as a refresher, your protons are positive, your electrons are negative, and your neutrons are neutral. And then your protons and your neutrons are in the nucleus of the atom. And your electrons are a lot smaller than your protons and your neutrons, and they are orbiting the nucleus. Orbiting nucleus. And then, of course, depending on the element, you're going to have different numbers of protons, neutrons, and electrons. So just a quick refresher too on atomic number. Atomic number is the number of protons that element has. So that's on your periodic square. So if you have a little periodic square and it's carbon and it's 6, that's the atomic number. Atomic number. And then down at the bottom will be another number. I think it's like 12 point something. That's your atomic mass. And your atomic mass is also equal to the neutrons plus the protons. So to find the atomic mass, all you need to do is, to find the number of neutrons, all you need to do is take the atomic mass and subtract the atomic number, and that will give you the number of neutrons. For the lower ones, usually about equal to the number of protons, but once you get into like higher elements and stuff like that, and even some of the lower ones, it's not exactly equal. So that's a quick refresher on atomic number and atomic mass. Okay. Here's just some chemistry jokes. I don't get to use them very often because I teach biology, but here's a few just little funny ones. Hee hee hee. And then a salt because sodium and chlorine together make sodium chloride, which is salt. So good times. So, all right. So keeping with the topic of atoms and how they work and what they're made of, the nucleus is the part that determines what the atomic mass is, which I just said that neutrons plus protons equals the atomic mass. And then the electron mass is so small that it doesn't actually really even factor into the atomic mass. So when you think about it, you're like, okay, neutrons are neutral. They're just kind of there. Like, what's the point of them? Like, why do we even care? The reason is that if you change the number of neutrons, you actually affect the radioactivity of the element and of the atom. So that's why it's important for stability. So I'll say neutrons are important for stability of atoms. Different number can lead to radioactive decay. Which is actually why carbon-14 can be used for carbon dating because it's an isotope that is unstable. So it breaks down and its half-life can be used to tell you the absolute age of a fossil or a preserved organism. So, okay, the electron cloud has your different energy levels, and the number of electrons that are in the outer shell, which is called the valence electron shell, is what determines the ability of your atom to bond with other elements, which is going to be really important for us in a few minutes here. And yeah, so your valence shell is stable when it has 8 electrons. Stable when 8 electrons. So also the number of electrons that an element has in its outer shell will determine how it likes to bond. And we'll talk more about that in a second. 2 other words that we're going to want to be familiar with are isotopes and ions. Isotopes happen when you change the number of neutrons. And ions happen when you change the number of electrons. If you change the number of protons, you become a different element. So that's why neither of those things are related to that. For ions, if you add electrons, you become a negatively charged ion. And if you lose electrons, you become positively charged. And this is where cations and anions come in, which if we go back up here to my jokes, you can see that they're positive because they have pause, not really what cats do. So that's how you can remember that cations are positive and anions are negative, which there's no like fun, cute way to remember that. But if you can remember cats, then you're good. All right. And I'll just put on here that an example of an isotope is carbon-14. The reason it's called 14 is because the mass is 14 instead of being 12. Okay. So now let's talk about bonding, which are also called atomic interactions. Some of them are not going to be strong enough to really be called a bond. So interactions is a more inclusive word of all the types. When we bond, we're trying to get to the octet, which is a fancy way to say that we're trying to get to 8 electrons in the outer shell. And there are a few ways to get there, either by sharing electrons or by giving them away or by receiving them. And those are the different types of bonds. In order to make bonds happen, there are chemical reactions. Just a friendly reminder that your reactants are always on the left side of the arrow and your products are always on the right. It's going to be important when we get to talk about photosynthesis and cellular respiration down the road. 2 types of bonds that we're going to talk about first are ionic bonds and covalent bonds. In ionic bonds, electrons are transferred. From one atom to another. In covalent bonds, electrons are shared between atoms. Now, in biology, we consider covalent bonds to be the strongest bonding type. I'll put that down here, that these guys are the strongest bond type. Now, like from chemistry, you might have a different opinion about that, but I'm just going to tell you that for biology purposes, covalent bonds are the strongest ones in your living organisms. Ionic bonds are strong too, and in chemistry, you might have experienced that they're really strong, but for us today and for the rest of the year, covalent bonds are the strongest. Okay, 2 different types of covalent bonds that we have to talk about are polar and nonpolar. So polar covalent bonds mean that the electrons are going to be between the atoms. So because of that, one of the atoms will be partially negative. That's the one that's pulling harder on the electron, so it will have the stronger electronegativity. Things like oxygen and chlorine have really high electronegativity, so they're usually going to be more negative in a polar covalent bond. And then one will be partially positive. And that's the one that has a weaker pull on the electrons. One important thing just to say is that the entire molecule will be neutral. So the whole thing is not positive or negative. The entire thing is neutral, but within the neutral molecule, there are regions of it that are more negative or more positive, even though the entire thing is neutral at the end of the day. So here's an example with water. Water's right here. This whole water molecule is neutral. So the whole thing is neutral, but the oxygen pulls a little bit harder, so it's partially negative. And the hydrogens don't pull as hard, so the electrons farther away from them, so they're partially positive. And we'll talk more about this in our water video in a few minutes. There's also this cartoon example of hydrogen and chlorine. Just as a nice visual, if you are more of a visual person, that the chlorine, because of its electronegativity, is pulling really, really, really hard on those electrons. And so it's more negative because the electrons are closer to it. And the hydrogen is more positive because the electrons are further away. So that's your polar covalent bond. Nonpolar is just the opposite. So in this one, the electrons are going to be shared equally. Shared equally between atoms. Often these are your like diatomic molecules because they are the same atom. So of course they're going to pull equally hard. So like oxygen gas, O2 is going to be nonpolar. Also most hydrocarbons, carbon is not super electronegative, so it doesn't pull much harder than hydrogen does on the electron. So things like fats and oils and waxes are usually always nonpolar. And then there's a little image here of your two like happy little hydrogens, and they're sharing equally, and everything's going great for them. Hooray! So they both would be, the whole thing is neutral, and also they are neither positively or negatively partially charged. Down here is a hydrocarbon chain, which we'll talk more about when we get to biomolecules, but also would be nonpolar, which is why water's polar, fats are nonpolar. So if you put oil in water, they repel each other because they're bonded in a way that's not compatible. So there you go. Okay. Next, I have a few more little cartoons. Oh, wait, not yet, but they're coming. So let's talk about the weaker bonds first. These weaker bonds are really important for cells to be able to signal to each other, which is like a major reason that you are able to stay alive, is your cells' ability to talk to each other about what's going on in your body. So these bonds in biology are only going to occur when the molecules or the atoms are close to each other. The first one is an ionic bond. So this is, we already kind of talked about it, but electrons transferred between atoms. This is important for salts. Hydrogen bonds are going to happen in polar covalent bonded molecules can interact because the partial positive attracts the partial negative. And I'll talk about this specific to water, which is really what we care most about it for. It gives water all of its like really special properties, but the partial negative of the oxygen and the partial positive of the hydrogen are attracted to one another. And that creates this pretty weak interaction that's constantly like breaking and reforming, which is the reason that water has these like impressive surface tension abilities, and like specific heat is really high, and like a lot of cool things about water are because of its ability to hydrogen bond. And last one is called van der Waal interactions. These are super, super, super weak. And these are temporary interactions caused by shifting of electrons. And actually, the coolest thing about van der Waals interactions, and like the only reason we're going to talk about them, is that they allow geckos to climb up walls. That's like the molecular interaction that their little toe hairs use, so they can like climb up the wall. So I linked this video to your OneNote that talks about how scientists are working on engineering like fake gecko feet, basically, to make robots that can like climb walls and crazy stuff. But I put that there if you're interested. So there it is. All right. So again, the weak interactions were ionic bonds, which I know, like if you're from AP Chem, I'm sorry, but in biology they're weak. Hydrogen bonds and van der Waals interactions. So now I have my little cartoons just as sort of like a review. I know these are really cheesy, but I do think it's helpful. So okay, so here's an example. There's these two girls. The girls represent atoms. Emily is like, I'm sweating. I'm so hot. I really wish I could get rid of this blanket. Sarah's like, I'm so cold. I'm unstable. Unstable because she's an atom. I wish I could like have a blanket. So they're like, oh my gosh, we can both be like stable and happy if Emily gives her blanket to Sarah, and now she's like, they're both comfy and their temperatures are stable because they have like 8 electrons in their outer shell. This would be an ionic bond. Because Emily is literally giving the blanket away to Sarah and Sarah is receiving it. So if it were an electron after this like transaction, Emily would be more positive. She would be positively charged cation, and Sarah would be negatively charged. She would be an anion. I guess we should have made her like frowning, but she's stable, so she's happy. Okay. This one, Emily and Sarah are both unstable. Again, they're both unstable in the same way. They're both cold. They're like, oh my gosh, let's like pick up this blanket and share it. So this is a covalent bond. Because they're sharing. And more specifically, it would be a non-polar covalent bond because it looks like they're sharing pretty equally. So one of them's not pulling harder than the other. So that's just a little visual to kind of help you if you were feeling a little lost in the sauce about bonding. All right, before I end this video, I'll just show you this picture of a hydrogen bond and what's sort of happening here. The dotted line in the middle is the hydrogen bond. So whenever you see pictures of this or are drawing a picture of it, hydrogen bonds are demonstrated by dotted lines because they're weak. And covalent bonds are demonstrated by solid lines because they're strong. So this line here is a covalent bond. And same with the ammonia. You also have these little symbols around the molecules, and those are showing that they're partially or negatively charged, partially positively or negatively. So the symbol is partially positive, and the symbol is partially negative. And again, it's just partial because the entire water and the entire ammonia is not positive or negative. And you can see that even by just looking at like, it's not H2O plus, it's just H2O. And same thing, it's NH3, not NH3 plus or minus. The whole thing is neutral, but within the neutral one, they're pulling different amounts, which is causing certain sides to be more negative or more positive. That's hydrogen bonding. And this bond would be constantly breaking and reforming between new molecules all the time if it was a liquid. If it's a frozen substance, then the hydrogen bonds are not breaking, which we'll talk about when we talk about water. All right, so that's going to be the end of this video, so you can kind of like take a break and catch up and regroup or whatever you need to do. But that is chemical bonding basics, quick chemistry review. And if you have any questions or if you feel like any of this stuff was like totally new to you, let me know and we can work on it together. So come back for part 2 when you're ready to watch the second part, and have a great day. Bye.